Part C, asymptotic notations. So this part, this topic, very abstract. Yeah. So this is the most abstract topic in this class. Yeah. A little hard to understand. Yeah. But only this concept, very abstract concept. Other than this one, all the other concepts are not that hard to understand. Yeah. All right. C.1, Introduction to Asymptotic Notations. Yeah. First, let's start with limits of two growth functions. So we did in our Monday's class. Yeah. All right. Now, let's revisit this topic. Yeah. When we calculate the limit of the ratio of two growth functions, we want to see how many cases do we have? How many different cases? Now we want to study those cases. Yeah. All right. So here we consider this limit where n goes to infinity, two functions, the ratio of two functions, f of n, g of n, yeah, corresponding to two growth functions. Now, typically, there are four different cases. Yeah. Look at these four different cases. The first one, the ratio, the limit equals 0. Second, C in our algorithms context, C should be a positive constant. Okay, positive constant. Yeah. 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 Because our f function, g function both come from our efficiency functions, and we use the counting numbers. We count the number of basic operations. So their values must be positive. Yeah. So the ratio of two positive functions, yeah, C must be a positive number, yeah, constant. Yeah. The third case, infinity. Yeah. There is case number 4. None of the three above, yeah, other, yeah, so we will look at case number 4 later. Yeah. After we finish our discussion on the first 3 relatively simple cases, then we study case number 4. Yeah. All right. For these 4 cases, so let's look at the meaning. Yeah. The representation. So what phenomenon can we find from these 4 cases? Yeah. Yeah. Let's look at one by one. Case 1. Yeah. Ratio of the limit of the ratio goes to 0. 0. So based on your intuition, so you can see the ratio goes to 0. That means the denominator dominates the numerator. Sorry, right? Oh, sorry. So, yeah, right. Denominator dominates the numerator, right? Yeah. Or the denominator function grows much faster than the numerator function, right? Yeah. So that's the, the trend like that. Yeah. But we like to use, some concept, yeah, some special concept to describe this phenomenon. Yeah. The concept we use here is we call the order of growth. Yeah. Order of growth of a function. Yeah. Order. There is some order thing. Yeah. Degree, order, in math. So we frequently use, these two words. The order, if you go back to the polynomial topic in our module 1 part B, so we have this concept, the order of a polynomial, right? Another concept we can also call degree of a polynomial. So two different concepts regarding polynomials. So here we have this order concept. We call it order of growth of a function. So you may ask me how to define order of the growth, right? So here, usually there is no clear definition for this order growth. People talk about, but this concept is treated like some imaginary number. But I figure out, so there is some simple way we can use to define this concept. I will give you that one later. Order of growth concept. All right, so here, the order of growth of f function is strictly smaller. Not equal. We exclude the equal case. Strictly smaller than the order of growth of g function. So that zero, limit zero, tells us this information. Here, although at this point we do not have the clear definition of this order of growth, but we know, at least we know, g function grows much faster than f function, significantly faster. So not just slightly faster. All right. Case 2. Ratio positive constant c, the limit. Positive constant. In this case, we say these two functions, they have same order of growth. So here, try to feel about it. The c, we only require c greater than 0, and we don't care if c, how large is the c, right? No matter c is 1 million or 1 millionth, okay? One very small number or very large number, if it is non-zero, if it is positive, then it doesn't matter. Both functions, they have the same order of growth. So we need to understand this point. So if you want to ask me, how do you make that c constant a non-factor here, right? It's not important. If the ratio is a constant, the value of the constant is not important here. If you want to ask me that question, so then I want to go back to my explanation I gave you in our Monday's class. Remember, in our Monday's class, I talk about characterization, right? So we want to use different categories to represent all the efficiency functions. And when I talk about, so how do we put those classes in one particular category? I said, if a function is scaled by any constant, non-zero constant, must be, let's say positive constant. If a function is scaled by any positive constant, c, then they are in the same category. Here you can see this order of growth. That means the two functions if they are in the same category, yeah, same category, because we can use C scale, appropriate scale number to, convert one function to the other one. Yeah, scale up, scale down, right? Yeah. So then these two functions, they must be in the same category. Yeah. So that's the we talked about last time. Yeah. So here you can see if they are in the same category, then we can say they have the same order of growth. Yeah. And another thing, so remember the last time we look at the ratio T of 2n over T of n, right? Yeah. But when you look at this ratio, so here we change to f of 2n over f of n, the first ratio. Then second ratio, g of 2n over g of n. Okay? When you compare these two ratios, you can see if we are in the second case, that C constant is cancelled out. So for that reason, the value of the C is not a factor. Okay? Cancel out. So you can also understand in that way. Then you can have another understanding like this. So actually the ratio like this closely related to the order of growth. Order of growth. Yeah, order of growth. This ratio, this special ratio, closely related to the order of growth concept. All right. Case number 3, infinity. Infinity, this time the numerator function dominates the denominator function. Right? Just opposite of case 1. Opposite of case 1. Or you can see in this way, if you take the reciprocal of case 1, you will get case 3. Or the other way around, if you take the reciprocal of case 3, you will get a case 1. Okay? So we have this understanding. The order of growth of numerator function, numerator function f of n is greater than order of growth of the denominator function g of n. So that's the first 3 cases. It's very easy to understand. All right. Before we move to case number 4, first, because let us improve our discussion a little bit. So, what do we mean? Because here, when we say these 3 statements, here you can see we need to write a lot of words on the screen, right? A lot of words. So we like to have a concise representation. Because the representations we use here relatively long. So we don't want to write so many words every time. So we want to introduce some compact notations here. So that notation, later we will call asymptotic notations. All right, what's that? Case number 4. Case number 4, here, let me tell you, before the discussion, let me tell you what's that case. The limit does not exist. Right? The limit doesn't exist. Okay? It's possible. Yeah. When you learn calculus, you need to consider this case, the limit does not exist case. Yeah. Okay. All right. Yeah. So now let's look at the compact notations, the so-called asymptotic notations. Yeah. For case 1, here we use this little o, our first asymptotic notation. Yeah. The definition, the understanding, the meaning of asymptotic notations, I will use, formal definition. Later, I will use a few slides to understand the exact meaning of these asymptotic notations. Yeah. Here, first, the notation part, we say f function belongs to little o of g function. Little o. Yeah. So our first asymptotic little o notation. Okay. What's the meaning? Little o. Yeah. So you just you can go back to case 1. The limit of the ratio equals 0. Yeah. Another this order of growth representation. Yeah. All right. Then for case 2, we use our second asymptotic notation. The f function belongs to capital theta. Theta. Yeah. That's the meaning. The same order of growth. Yeah. So we use capital theta to represent. Yeah. So here the asymptotic notation, this representation, big theta of g function, this representation, yeah, we understand it. We understand this representation as a set of functions. So it's a set. Yeah. It's mathematical object. It's a set. Okay. It's a set. Yeah. Yeah. A set of functions. Yeah. Yeah. A large set of functions. Yeah. Set. Okay. So each asymptotic notation represents a set of functions. Yeah. All right. Third one, our third asymptotic notation, little omega notation. Little omega. Okay? Yeah. So here we use little, later we have big version. Okay? So this little o, later we have a big O version. This little omega, later we have a big omega version. Okay? So the meaning different. Yeah. Yeah. So here we have two little symbol asymptotic notations. All right. Then case number 4, the limit does not exist. Yeah. So we need to understand this special case. Yeah. All right. In this case, we cannot calculate. Yeah. So your calculation, when you try to calculate the limit, you will fail. The limit does not exist. Yeah. So that means the L'Hopital's rule won't work, right? Yeah. Remember the L'Hopital's rule, the powerful tool we used in our last class. It will fail. Yeah. All right. Now let's learn this, why it's possible the limit does not exist. Okay? So you want to understand why the limit does not exist. Okay? So here I can give you a simple example. Yeah. So I show you a simple example, and in this example the limit does not exist. Yeah. Right. All right. So here let's consider this case. All right. Limit n goes to infinity. Yeah. All right. Two functions, numerator, denominator, two functions. Okay, all right. The numerator function first, n And yeah. All right, so let me use this. 3 plus -1 to the n times n squared plus 1. How about this function? That's our numerator function. Okay? All right. The denominator function, let me write this way. 4 minus -1 to the nth. N squared minus 1. How about that? Okay? So let's consider the ratio of these two functions. Okay? Yeah. All right. Let's try to calculate. Okay? All right. There are two parts. Yeah. The structure of both functions are similar, but in the first pair of parentheses, slightly different. Yeah. The second part, you can see the second part, 1 n squared plus 1, another n squared minus 1. Yeah. And these two representations are very close, right? The difference is very small. Yeah. And when we make n goes to infinity, so here n goes to infinity, all right? So these two numbers should be very close, right? Yeah. Yeah. Very close. Yeah. So if we, many times in order to see they are pretty much the same, people usually do division by n squared. Okay? Yeah. Both numerator, denominator do division by n squared. Okay? Yeah. Two brackets. Yeah. You can see for these two brackets, let me just simplify the first one. 1 plus 1 over n squared. Okay? All right, the first. The second, 1 minus 1 over n squared. Okay? So we compare these two representations. Think about when n goes to infinity, that 1 over n squared, 1 over n squared, all have limit 0. So it's gone. Yeah, the limit is 0. So only one left. One left, then nothing, right? Yeah, 1 times anything is anything, right? So yeah, both brackets become 1. Okay, all right. Both become 1, so we can simplify to limit infinity. So then 3 plus -1 to the n, 4 minus -1 to the n. We calculate this simplified limit. Yeah. To calculate simplified limit, so now this time we need to plug in n values. N values. All right. Yeah. So let's see the trend. Yeah. The ratio. The trend for the ratios of this expression. Yeah. All right. So when n equals 1, 1. So 3 minus 1. That's 2. 2 over 1. 4 plus 1. Right. 1, so here 2, we want to do experiments on consecutive integers. So if it is 1, so the numerator 2 over 5, okay, 2/5. If it's 2, then 3 plus 1, so 4 over 3. So the bottom 4 minus 1. Okay, so 4/3. Then 3, odd number, right? So if it is odd number, we have 2/5. If n is an even number, we have 4/3, and so on. Okay, so these two fractions appear alternatively in this pattern. Okay, yeah, yeah. Two constant numbers, two different constant numbers appear alternatively in the sequence. Yeah. Now I ask you, what is the limit of the sequence? Yeah. So we want to calculate the limit of the sequence, and we observe the pattern of the sequence. Yeah. Only two different values, up and down, up and down. Okay, all right. So the result is no limit. Or you say the limit does not exist, because this sequence does not converge. If the limit exists, the sequence must be converged, right? Converge to one number, not two numbers. Two numbers you cannot call converge, right? Yeah. You cannot call converge. Yeah. Only one number. Only the sequence close to one number, then you can call converge. But here, the sequence close to two different numbers, so diverge. So we call the sequence diverges. It diverges, so we say the limit does not exist. Yeah. That's the case number 4. Well, the limit does not exist. So we cannot use our powerful limit tool to study the ratio to compare two growth functions. Our limit method does not work. So we have to drop this method. Yeah. So we need to find a different method. Yeah. So the new method should not rely on the limit concept. Yeah. No limit there. Yeah. Yeah. So next, so we need to look at the new method. Okay, all right. Yeah. All right. Objective. Yeah. Even if the limit does not exist, we can still compare growth functions. Yeah. Okay, yeah. So that's, but we need to find a way to do it. Yeah. Yeah. So we want to compare without using the limit tool. Yeah. All right. How to do it? Yeah. So the function g of n is usually a simple function. Yeah. Because when you look at the expression, the g function appears in the denominator, so we use it as the base function. Yeah. We use g function as a base function. So all other functions we use to compare with this g base function or reference function. Yeah. But when we choose a base function or reference function, we want to make it as simple as possible. Okay? Yeah? So we want to drop all those minor terms. Yeah. Remember? So the last time we do 2 rounds simplification. Yeah. The first round, we drop all the minor functions. Yeah. Second round, we drop the leading constant. Yeah. Yeah. So those functions we call growth functions. So here we want to use growth functions for the denominator g function for comparisons. Yeah. All right. Yeah. Then now we use g function because g function must be known first. Okay. Yeah. So then we use g function to measure f function. Yeah. The g function to help us, get more information about f function. All right. Yeah. Complex. Yeah. So here, we should understand complicated function. Yeah. Yeah. Because in math, complex there is a special meaning of complex. Complicated. Okay. Complicated function. Yeah. Not a real complex. That meaning. Okay. All right. There. How do we use g function to measure f function? Yeah. So the simple way, we use constant multiples, yeah, or positive constant. Remember our little c, positive constant multiples of g function to approximate f function. Yeah. All right. That's the natural idea. Yeah. Because from the previous slide, 2 slides, the positive constant multiples of g, so all those functions belong to the same category of g function, right? Yeah. Yeah. So you scale g function by any positive constant number, yeah, up, down, those functions are in the same category. Yeah. Here, we use functions in the same category to approximate f function. Okay? Yeah. That idea. Yeah. All right. Specifically, can we find 2 positive constants C1, C2 such that this inequality holds? C2 multiple of g function less than equal to f function and less than equal to C1 multiple of g function. Okay? One upper bound, one lower bound. Yeah. 2 sides approximation. Okay? Yeah. From both sides. Yeah. From the lower bound side and upper bound side to approximate f function. Yeah. If we can do that, yeah, because these 2 functions are in the same category of g function, right? Yeah. Can we say f function is also in the same category of that g function? Yeah. Yeah. So that's the reasonable conclusion, right? Yeah. Yeah. And this method, because when we use inequalities, yeah, 2 inequalities here, we do not need to look at the limit, right? Yeah. Yeah. Even if the limit does not exist, we can still use this inequality method to provide us information about 2 growth functions, f and g, 2 functions. Yeah. Okay, all right. Yeah. Then, now, with this new, comparing with the limit method, so this inequality method. Yeah. Next, now we can define asymptotic notations. C.2, define asymptotic notations. Yeah. All right. First one, big O notation. Yeah. So we learned a little O before, right? So this time, that's the big O version. Yeah. All right. Yeah. The meaning is different from little o. Yeah. Big O. Yeah. So what's that? The definition. All right. For a given f function, given function g of n, the notation big O of g of n represents the set of functions all those fn functions that satisfy the following condition. Okay, so following inequality. Yeah. There exists some positive constant c. Here we only need 1 constant. Yeah. Positive constant c and some non-negative integers n 0. Yeah. Another special number is also needed to represent a new condition, such that this inequality f of n less than or equal to c times g of n for all n greater or equal to this n0 number. Okay? Yeah. That's the definition of big O. Here you can see the main part of the condition is this inequality. Here you can see when we talk about big O notation, we only look at the upper bound of f function. We do not look at the lower bound. Yeah. Only upper bound. Yeah. That's our main condition. Yeah. After this main condition, yeah, so there is a small restriction. We also need to pay attention. The small restriction is you have to find some special number, yeah, and we only require this inequality hold when n greater or equal to this n0 number, n naught number. Okay, all right. That means if n less than this n naught number, we do not require this inequality hold. Okay, yeah, yeah. Even if the inequality does not hold when n less than this some special constant number, yeah, we don't worry. Yeah. We don't treat it as a violation. Yeah. Yeah. We only worry about, so here, this inequality, usually people say n is sufficiently large. Sufficiently large. In math, yeah. In math context, people like to call n sufficiently large. Then, because when they use this phrase sufficiently large, they do not need to mention this n naught number. Yeah. Yeah, it's not important. Yeah. Yeah. They don't need to mention it explicitly, just say sufficiently large. Now, what's the meaning of sufficiently large? You can find some special integer. Yeah. Then when n greater than that special integer, then your inequality holds. Yeah. All right. Yeah. Yeah. But here, this for this n0 number, before you select it, you have freedom to choose what is your n0 number. Now, you have freedom. Now, n0 could be 1 million, 1 billion, or 1. So you have freedom to choose this n0 number. Okay? But after you select it, then you have to fix it. Yeah. After you select that n0 number, then when n changes, we know this n is a variable, right? Yeah. We allow n change all the time. Okay? But when n changes, this n0 never changes. After you select it, you fix it. Okay, we always use that same n0. Yeah. Yeah. All right. Okay. Yeah. So that's our understanding of this formal definition of big O notation. Yeah. All right. Then let's look at the graph. Yeah. The graph here. Yeah. Our target. We want to approximate this f function. So we have a graph of this f function. Yeah. Then the g function, yeah, g we know it's a relatively simple function we use to measure f function. Yeah. Now, the way we use to measure g function, we use the constant multiple g to approximate f from the upper bound. Okay? Yeah. Yeah. From the, above. above the graph of G. Yeah. Then you can see bounded above f function, but this vertical line and zero line, the left hand side of this vertical line at n0 point doesn't matter. Doesn't matter. Doesn't matter means if you go left hand side, the graph lower, f function graph higher, it's not important. Okay? It's not important. Okay? We don't worry, it's not important. Yeah. Why it is not important? Yeah. Why it is not important? Yeah. I will explain later. Okay? After we finish all the definitions of these asymptotic notations, let me explain the reason altogether. Yeah. Because for each definition we have the same thing. Okay? Yeah, we have the same thing. So I will explain only once, covering all the asymptotic notations. Yeah. All right. Yeah. This is big O notation, the definition. Yeah. Second one, next one, big omega notation. Yeah. Now similar. So we spend a lot of time to understand big O notation, but after that we have some background. Yeah. So we have some basic understanding. Yeah. Then we only need to change our basic understanding slightly. Yeah. Then we can get understanding of other asymptotic notations. The next one, big omega notation. Yeah. So the most part, the wording, most part the same. Yeah. The main part, the main difference part, inequality. Inequality, that's the main difference part. Okay? Yeah. So now the meaning, big omega function, then we need to, this time we change to C constant multiple G, we use it as the lower bound function to approximate f function. Yeah. Approximate f function from below. Okay? Yeah. Yeah. So upper version and the lower version. Here we use this lower version, big omega. Okay? Then all the remaining part the same as the one of big O notation. Yeah? Yeah. We only change the inequality here. Yeah. All right? Then it's also sufficiently large. Yeah. From the graph you can see we approximate f function from below using the C constant multiple of G function. Yeah. From below. Yeah. Yeah. All right? Yeah. Yeah. One up, one below. Yeah. Then the next one, yeah, automatically from both sides, from both up and down. Yeah. Two bounds. Yeah. Upper bound, lower bound. Two bounds. Yeah. That's we call a big theta notation. Yeah. We saw it. Our case too, big theta. Yeah. But here we want to give the formal definition of big theta notation. Yeah. All right. So, all right. So the setup here. Then the main difference this time we need a two positive constant, C1, C2. Excuse me. All right. So then upper bound, lower bound. Yeah. All right. Sufficiently large also. Yeah. The graph. Yeah. Two side approximation. Yeah. All right. Yeah. So you can see. Yeah. These three asymptotic, that's the most frequently used asymptotic notations. these three, okay? Yeah. Yeah. So these three actually, these three are the most frequently used asymptotic notation, only two of them. Yeah. Big omega is rarely used. Yeah. Not that frequent. Yeah. So most frequently used, one is big O notation. Then another one, big theta notation. Okay? Yeah. So these two most frequently used. Now, all the others are rarely used. Okay? Are rarely used. Yeah. So you after you understand their meanings, yeah, so you only need to focus on these two. Okay? Yeah. That should be enough, yeah, in our discussion most of the time. Yeah. All right. Yeah. So we finished the formal discussion part. Yeah. All right. Next, C.3, examples of asymptotic notations. In order to understand better, so we need to work on some examples. Yeah. From simple examples, then relatively hard examples. Yeah. Yeah. All right. Yeah. So here I select several examples. Yeah. All right. The first example, yeah. 2.1, yeah. F function very simple. N plus 2. So simple. Yeah. And the G function, only N. Yeah. Big theta of N. Yeah. Now, you need to write a proof. Yeah. Show that, write a proof. Yeah. Yeah. So it is a math question, right? It's a math question. Yeah. So for this class, yeah, I use these math questions for understanding. Okay. Yeah. So in my homework assignment, I won't give you this kind of math questions. Yeah. Typically for understanding. Yeah. All right. Yeah. To show, here we use big theta. Yeah. There are two different ways. Yeah. Because here we are talking about big theta asymptotic notation. There are two different ways we can do. Yeah. The first one, limit way, right? Yeah. Limit way, our case number 2. That's the limit way. Yeah. We can prove it. Yeah. The second way, the definition way. Yeah. We have the formal definition, upper bound, lower bound, so we can use to check if we can find C1, C2. Yeah. For upper bound, lower bound. All right? Yeah. So let me show you quickly, yeah, because this question very simple. First, the limit way, yeah. Let us just take the limit. Okay? Yeah. F function we put at a numerator. G function we put at a denominator. Okay? All right. Simplification a little bit. 1 plus n, 2 over n. Right? Sorry, 2 over n. Yeah. And when n goes to infinity, the fraction in the second term goes to 0. So 0 plus 1, it is 1. Okay? 1 is a positive constant, right? Yeah. Positive constant. That corresponds to our case number 2. C, little c is a positive constant 1 here. Yeah. So we make our conclusion. Yeah. N plus 2 belongs to big theta of n. That's the first method, the limit method. Yeah. You just calculate the limit. Okay? All right. The second one, we need to use definition. Upper bound, lower bound. Yeah. Let me show you how to do the definition way. Yeah. All right. First, let us write out f function. Yeah. Then, we calculate upper bound, lower bound separately. Yeah. Which one easier? Yeah. So when we start we want to do the easier case first, right? Easier case first. Yeah. The lower bound case easier. Because n plus 2, if we drop that 2, the function value becomes smaller, right? So we get a lower bound. Yeah. N plus 2 greater than n for any n. Yeah. For any n. Yeah. But our n, so here, when we consider in the question, we consider n greater or equal to 0. Okay? Yeah. So we start from the 0. Yeah. We do not consider n negative number case. Yeah. Yeah. So the smallest possible number for n is 0. Yeah. So here we put a condition, n greater or equal to 0. Yeah. Then the lower bound, this inequality holds. Yeah. So we have the corresponding coefficient for the lower bound, C2. C2 here we select 1. C2 times n, so 1 for C2. Yeah. So we complete the lower bound part. Then upper bound. Yeah. Upper bound slightly harder than lower bound, but not too much harder. Okay. The upper bound, this time we need to find the C1, and we want to use C1 times n to be an upper bound for n plus 2. Yeah. It is simple, yeah, but you need to fix all the details here. Yeah. All right. So what C1 you want to use here? Yeah. Here. Yeah. Yeah. Let me show you the formula transformation here. Yeah. All right. Here we replace 2 by n, and we hope to get a larger function value. Yeah. We replace 2 by n, but we hope the new function value should be greater or equal to the old one. Then we need some condition, right? Yeah. We need some condition. Because it may not be always true. Sometimes it is not true. For example, when n equals 1, it's not true, right? Yeah. So we can put some condition here to make it true. Yeah. So the condition we put here is n should be greater or equal to 2. Yeah. When n is greater or equal to 2, then after we replace 2 in the f function by n, we get a larger value. Yeah. Because the larger value we can use as the upper bound. Okay, all right. So n plus n, 2n, that is the upper bound. Okay, yeah. So n plus 2 less than or equal to 2n, 2 constant, positive constant, it corresponds to C1. So we choose C1 equals 2. Yeah. So we find both upper bound, lower bound. Okay, yeah, all right. Then, so if we, because we need to compare what we are doing with the original definition. Yeah. So we address C1 constant, we also address C2 constant, and another thing we need to address, the n0 number. Yeah. So we have both bounds under what condition, right? Yeah. So here, our condition should take care of the both cases. Yeah. Our condition should cover both cases. Yeah. So then you can see if we cover n greater or equal to 2, then it automatically covers n greater or equal to 0, right? Yeah, because n greater or equal to 2 implies n greater or equal to 1. Then we can drop this condition, right? Yeah, because we want to make our condition simpler. Yeah, okay, condition simpler. Yeah, yeah. So our final condition, we only need this one, n greater or equal to 2, and we make that 2 as our n0 number. Okay, yeah, this n0 number. So we find that special n0 number. So when n0 equals 2, then for n greater or equal to n0, yeah, we have both upper bound, lower bound, C1, C2, constants. Yeah. All right, that's the first question. Okay, all right, yeah. Here, before I move to the second, I want to make some comments, yeah, a little bit, yeah, yeah. Because here our f function very simple, very, very simple. Okay, all right. Sometimes our f function could be a little harder. Yeah. For example, our f function becomes n plus 2 cube. Yeah. We want to show this function belongs to big theta of n cubed this time. Okay? Yeah? Similar idea. Now, one way you can take the limit. Okay? Very easy. Yeah, just cube. Okay? The cube of 1 also 1. Yeah. So you can prove it easily. But the second way, here I want to make some comments for the second way when we apply upper bound, lower bound, C1, C2 constant. Yeah. When we do that, yeah, one important step, many students may make that kind of mistake. Yeah. Because I gave this kind of questions in my homework assignments before. Yeah. Although recently I rarely give. Yeah. So I noticed many students, they expand this function first. That's not a good idea. Okay? Yeah. You need to apply some, binomial formula, expand it. Yeah. N cubed plus 6, 3, right? Yeah, 3 times 2, so 6n squared, yeah, and 12n. Yeah, you know that formula, okay? Binomial formula. Yeah. N plus 8, right? Yeah. So many people expand that polynomial in this way, but you can see after expansion, now if you want to find the upper bound, it becomes much harder, right? Yeah. Because how do you control the last 3 terms, right? Yeah. It's not that easy. How to control last 3 terms? Yeah. Yeah. It becomes relatively hard. Yeah. Yeah. It could be very messy. Yeah. It could be very messy. Yeah. So the best way, do not expand that. Okay? Do not expand that. Yeah. The best way is, yeah, we still do this way. Okay. Yeah. After you get this one, this inequality with this particular n0, then you raise both sides to cube, right? Yeah. Yeah, because we have the our basic inequality we raise to cube. Cube. Yeah. This one we know 8n cube. C1 constant. 2 cube. So you'll find the C1, 8. Yeah. That's very easy. Okay? Yeah. Much easier than that expansion way. Expansion way. Expansion way are very messy. Okay? Very messy. Yeah. That's just some comment. Okay? Yeah. So that means you should try to find some clean way, best way. Yeah. Yeah. Not messy way. Okay? Try our best. All right. That's the first question. Second question. Yeah. This time big omega, only lower bound. Okay? Only lower bound. You do not need to do the upper bound. Only lower bound. Yeah. Lower bound, you can see, very easy. Yeah. N cube, yeah, we know. They are non-negative integers, right? N should be non-negative integers. Yeah. So we can see this inequality hold for all non-zero integers. n. Yeah. So then we have C1. Yeah. Sorry, we only need one C. Yeah. C equals 1 and N0 is 0 by the definition. Yeah. So that's the second example. Okay. Yeah. All right. Yeah. Let me do another example, then we can take a break. Yeah. Third example. Yeah, third example, yeah, I just explained, okay, in the previous slide, okay. Yeah, I just explained. So let me quickly, lower bound, very easy, right? Yeah. C2, 1. Upper bound, 2n, so then we raise to cube, okay, raise to cube, so, yeah. Yeah, very easy, yeah. And do not expand it, okay, do not expand it, yeah. Because the expansion way, when your exponent is very relatively large, then you will, you will get a very nasty, right? For example, because I remember once I gave a question like raised to the 5th. Raised to the 5th, right? Yeah, if you still expand it, very messy, okay? Very, very messy. Yeah. But if you use this way, just 2/5, right? 32. Yeah. So your upper bound, C1, 32 times n/5. Yeah, n to the 5th. Yeah. Yeah. All right. But you don't need to worry. So the recently I never give you, this kind of math questions. Math questions. We only do understanding. Okay. We only do these questions for understanding. Yeah. All right. Let me see. Yeah, I still have a few minutes. Let me do one more example. Okay. Yeah. We try to do a little more. Yeah. Because this semester too short. Okay. This semester too short. I need to, cover the same material as the regular semester. Think about that. I need to cover the same amount of material. Yeah. So we do not want to get a, watered down class, right? So we want to get a, same material, same quality, yeah. Standard, same standard. Yeah. All right. Yeah. 2.4. This time we need to work on the log function. Okay. Little we know we have to use the limit way. Yeah. We have to use the limit way. That is our case number 1 we saw at the beginning of this class. Case 1. Yeah. Yeah. So here we need to prove that the limit equals 0. Okay. Yeah. Limit of the ratio of two functions, f function over g function. But here there is one important technical question. That is, this n variable is a discrete variable. Yeah. I mentioned last time, right? Yeah. Recall, so what do when we apply L'Hopital's rule, we know if a function of discrete variable function, there is no derivative. The derivative concept is not defined. It's not defined. You cannot use the derivative concept. Yeah. If you use it, yeah, so there is a hole. It is not a rigorous argument. There is a hole, theoretical hole there. Okay? Yeah. So we want to fix that hole. All right? For that reason, we need to do conversion. Yeah. The conversion is very simple. We convert this discrete variable to continuous variable. Okay? Yeah. So we just write here we can treat as two different functions. Yeah. Although two different functions, but these two functions are closely related. One is the continuous version, another is the discrete version, but the same function. Yeah. All right, so let's do the continuous version to calculate the limit. Yeah. All right. Log function, log of x over x. Here, x is a continuous variable, so we can use the derivatives of both functions. Yeah. So, all right. Then, we also need to check, in order to apply the L'Hopital's rule, we also need to check if the ratio is an indeterminate form. Indeterminate form. Yeah. And for this case, we only consider infinity over infinity indeterminate form. Not other forms. Okay, only one. Yeah. That form related to our algorithm context. Yeah. All right. It is, yeah, so it is, so here let me write infinity, our checking, okay? Yeah. It pass the indeterminate form checking. Okay, all right. Yes, then we need to do the calculation. Yeah, but here we assume the log base is a constant a greater than 1. Yeah. Greater than 1. Okay, all right. Then we can take derivative. Yeah. We can apply the L'Hopital's rule, taking the derivative. Yeah. So we apply the formula. Yeah. Denominator, we apply power rule, right? Yeah. So here, the power rule, power function. Yeah. So here, I want the power rule for the derivative, x to the r. Yeah. So r is a real number, some real number. Okay. Yeah. When we take its derivative, the power rule tells us we need to use r times x to the r minus 1. This is the power rule, okay? The power rule of derivative. Yeah. Here we apply the power rule, we get a 1. Yeah. Our little r is 1. Yeah. So we get a 1. Right. Then the numerator function, we apply, the formula of the log function. So that is 1 over natural log of base a. It is a positive number. Yeah, so we know because it's greater than 1. So this log function value is a positive number. Yeah. Positive constant. Then times variable x. Yeah. Then we do simplification. Yeah. After simplification, now our x variable is at a denominator, and when x goes to infinity, this fraction, the limit of this fraction is 0. Okay. All right, so we get the answer. 0 is the answer. Okay, 0 is the answer. Yeah. Then we go back to our original question. Yeah. All right, let's take a break. When you come back at 7 o'clock, then I explain the conclusion part.